Okay, so what we will do in the next session is walk through an example of how to write your concept-based generic library. And so we will apply many things of the last 2 days, and but on a relatively small, simple example. And the idea was designed by Anton, who did this session 2 years ago, and there's a nice video online, so you can rewatch that already. And as a starter, let's look at 2 quotes about concepts. So what are concepts? That means requirements on template arguments are a central feature of C++ generic library design. They define the terms in which libraries, generic data structures, and algorithms are specified. Every working generic library is based on concepts. These concepts may be represented using specifically designed language features. That's what you saw, the C++20 concepts. In requirement tables, as comments in the code, in design documents, or simply in the heads of programmers. However, without concepts, formal or informal, no generic code could work. So even without having the C++20 concepts, concepts are always there. And I think by now maybe you understand that, but I also have, again, a very simple warm-up example. And the other thing is, generic programming doesn't mean templates. It means generalizing algorithm implementations, iteratively discovering sets of requirements on the arguments, and grouping the requirements into named concepts and hierarchies of concepts. It's about algorithms, not templates. So it's basically, it's also what Alberto said at some point. So you start with some idea of your concept and you refine it by looking at what algorithms you apply to this concept. And this work, writing such a generic library, that requires some discipline, and we will look at some best practices on how to do this. And my warm-up example is again this, right? So what is the first thing here? What is the concept here? So it's called square. It's taking some t. And what is the concept? Is there a concept? Who thinks there's the concept? What is the concept? No, in the first box. Is in the first box? Is in the first box? Is there a concept?
I mean, according to this definition, yes, it's in the.
Yeah, I mean, it's in the head of a programmer in this case, right? It's because you cannot pass what you want. You have to pass something that you can apply the multiplication operator on it. So there's at least a syntactic constraint on that concept. Okay? It has to be multipliable. And in the second one, it's now constrained to only floating point types. And now we make very explicit what the concept is about, right? It's about multiplying floating point numbers. You might argue now it's maybe over-constrained because probably that function could also work for integers. Now I cannot do that. The last is another example. I introduced the concept has multiplication operator. Now I made the first implicit concept explicit. This is all I require syntactically. But there are also semantic requirements on concepts. There's stuff that you cannot express in C++ concepts, but they are still there. Right? So for example, in the second case, it's very clear, right, what I expect semantically from that concept in the case of multiplying it. So I expect that it does multiplication of floating point numbers. In the other case down there has multiply operator. I don't know, right? I only know it does multiplication, or it doesn't do multiplication. It applies the multiplication operator on this type. So this type could be a person. So I I don't know, maybe this operator creates from this person a pair of two persons. I can do this, and this concept has multiply up, doesn't say anything about it. So there are always these two aspects, something that you can put into code, the syntactic requirements, and there are semantics that you have to still specify somewhere in code, ideally, not in code, as comments in your code, or somewhere in documentation. And what we will do is I will live implement this generic library that deals with these kind of things. Here's one example of the things we are dealing with. It's called cursor. This is some cursor that has three functions: get, which returns a constref int, done, which returns a bool, and the next, which does something, right? These are the syntactic things, and what it semantically means you can probably already guess. And we do the break here, and you can think about this during the break. And we will start here somewhere. Okay, let's go. So we will implement this generic cursor library. And we do this on Compiler Explorer. We use a very recent version of GCC. We use C++20. And we do some good error messages. We want to see all the warnings, and we do enable some sanitizers to make sure that our code is fine. And hopefully we'll not need this. Okay, let's start with understanding our cursor idea a bit better. Let's implement a very concrete cursor. Let's put some stuff there. Let's put a vector of int and fill it with something. You're missing the vector include. And let's implement these functions. So what should get do? What do you expect it to have us? What do you expect to happen? Yeah, return in which one? I have in my vector, I have many. Let's return the one that we call at the index position. What is that? I put it here. Let's implement next. What should next do? Probably increment the position. And what should done do? The size, like if position is equal to the size of the array, we are done, right? So how can we use that? Let's implement a function that we call a dump. It takes a very concrete cursor. And it loops over it as long as we are not done. Then in the next iteration, I increment the cursor with next, and I print the value of the cursor. I'll put a separator here. And that's it. Maybe let's put this here. Sorry, this is too much. Right, this is what I want to do. So I want to print all the values that I can get from my cursor until we are done. Let's try if that works. Let's remove this. That looks good. So now we have written a very concrete dump function for a very concrete cursor, but it's obviously not how we want to write our dump function, because probably there are other useful cursors that we can pass to it. So let's put auto here, and it still works, right? So we accept now any type. But not every type will work. If I pass a 2 here, an integer, it doesn't work because on my integer I cannot call the member function done, next, or get. So we'll get this error here. I requested the member done, but it's not there. So this here, I think I'm not sure if someone mentioned this, abbreviated function template. So it's basically a C++20 feature, this auto here. You know it from lambdas, right there, you do it all the time, but to be able to do this on normal function is new in C++20. Previously, you would probably do something like this. Now let's remove this one. Okay, let's go back. We do C++20. Okay, now we have a bit of an idea what the idea of this concept is, right? So you require the concept to have these functions, and there are some semantic requirements. Probably you should not call next after you are done, or at least not get after you are past done, or something like this. This is all semantic requirements that we actually cannot encode in the type. But now let's write the syntactic requirement. So let's write the concept of a cursor, the C++20 concept. And we know how to do this. So concept cursor. So what is this? Let's start with something very simple. Let's require that our cursor is move constructible, so we can actually move it into other functions. So requirement that maybe makes sense. Is it a good concept for our cursor? I don't know. Let's try. Let's check if our very concrete cursor is actually a cursor according to this concept. Yes, it is. Let's check something else. Is integer a cursor? Looks like it is as well. So probably we should be a bit more specific. So let's put some more requirements on that thing. So we require that this type T, if we take it by reference, should have next, right? For example, let's say cursor. So cursor should have next. Okay, looks like very concrete cursor is still a cursor, int is not. Well, let's remove this. Now we're still not complete. We also want the cursor to have done and to have get, right? Does it make sense? I mean, it looks like our very concrete cursor is still a cursor according to the concept. This is nice. We can be even a bit more specific because we can also take a const cursor, and as you can see from here, the get and the done, they should actually not modify the content of the concrete cursor. It just returns stuff, checks stuff on it. So we can require that done and get should also be callable on the constant cursor. Next, not, right? Because what next does, it's not a const member function. It actually modifies some state in our very concrete cursor. Makes sense so far? Is the speed okay, too fast, too slow? Too fast, okay. So where are you?
I copied out this, but missed the initial inclusion.
Yeah, I mean, this, you can find all this stuff at the end in the repository, so you don't have to type it, but yeah, if you like, you can. And then you have to do my typing speed, so better follow the ideas. So okay, well, can we do more? Probably we can. So done most likely should always return a bool. So let's constrain or require that cursor done returns bool. So we can use, for example, same as bool. We can also maybe make it a bit more flexible and use the concept convertible to. So we can be allowed to return other things that are convertible to bool. I mean, it's a question, is that a good idea or a bad idea? Maybe you over-constrain. I mean, here, maybe not a perfect idea, because I mean, this still works now, right? So you can return int because it's convertible to bool. Maybe it makes sense, maybe not. So maybe let's keep that. We could now also think of more constraints, but maybe we figure them out later when we do stuff with it, right? Because now we have only a very concrete cursor, and we can basically constrain it to just allow this very concrete cursor, but then it's not very generic. So let's keep it like this for now. It's basically now done should return bool, next does whatever, get does whatever. I mean, this is our concept. Let's write some more interesting cursors. For example, let's write a cursor that is called numbers from. Let's template it on integrals, so you can use int, size t, whatever. And the idea is that this cursor returns, starting from some number, returns all the numbers. And so how does that look like? We put the current value, and then let's copy from here. So what should get do? Get should probably now return a t. Which t? The current value. What should next do? Next just increments the value. What should done do? probably return false because we have many numbers and we don't know when to stop. I mean, at some point we might overflow or whatever, but still probably makes sense. So let's see how we can use that. So let's dump numbers from, what should I do? Numbers from 2. Okay, it returns many numbers and it's actually truncated. The exit code of this program is not 0, so something went wrong. I mean, it's basically Compiler Explorer killed my program at some point because it's an infinite loop here. Right? We are never done. Okay, here's a small side note. In this, we are using 2 C++20 features. So what are the 2 C++20 features that we are using? Is an expert question. This is numbers from, right? What is this? Looks like a function. Is not a function, obviously. Right? 2 C++20 features. No, 20. Okay, okay, Mauro says 17 because he thinks we are doing class template argument deduction.
No, it's not what we do.
It's what we are doing, but it's only for aggregates, only works with C++20. What is an aggregate? Is some special things where you don't have to write a constructor. You can directly initialize that value under some conditions. So basically we are directly initializing this value. And we are doing class template argument deduction that you know from yesterday. So we pass it 2. This is an int. So instead of having to write explicitly the int here, I deduce it from the 2. What is the other feature? Aggregate initialization goes with curly braces, normally. But in C++20 you can use the other parentheses also nicely. How can we, one other small C++20 feature, what we can also do is this, right? Designated initializer is a feature that C had already some time. Now we can actually say, here we have to guess, right? We have to guess where does these 2 go. Okay, we look here, there's something called while underscore, it probably goes there. Now we can say, go there. If we have multiple things, then we can give it a name and it goes in the right place. We don't mess up. I don't know, let's go back to this. Actually, I missed earlier one point. Where can we improve our code now? Inside here. So I'm still taking any type, right? But now we have a concept, we can constrain this thing to only accept cursors. Nothing changes, hopefully. We also can do one more check if we like, if numbers from is really a cursor, right? But we know now how to do this. Numbers from, let's say, int is a cursor. Otherwise, we would have seen the error here as well, right? We can still try to do dump2 now. What will happen? So we get slightly different error. Now it says, okay, there's no matching call, no matching function for this call, because now we constrain what is allowed for dump. And dump is not a valid function anymore because it only takes cursor. It's not considered, but it says, okay, there is actually something that we could consider. There's a function called dump, but it says only cursors are allowed and this integer doesn't have next, for example. Okay, let's remove this again. Speed okay now? Are you still there? You're still starting slowly, right? Okay, so what can we do with these numbers from? It's not very useful because, I mean, it will run forever. Let's try to find a cursor that allows us to stop at some point. Let's call it take. Let's call it actually take impl because implementation thing now we will find a better name. We will use the take, the better name, take for something else. And what does this, should this take? It should take a cursor, C, and then we store it inside. And take should take n numbers from the cursor is the idea. So let's also have something that we call left. So how many elements are still left? And now let's implement these functions. So what should get do? So it should return something from this cursor, right? So it should return whatever this cursor is currently pointing to. Now what is this t? I don't know, right? Don't care. Auto. So it's whatever this cursor gives me. What should we do in next? Probably we should decrement left. Something else?
Don't you need to initialize lift?
Yeah, but I mean, I'm not using that class yet. So at some point I should initialize it. Well, I'm describing or defining this class, take impl now, and at some point I should put some cursor here and some value, how many are left. And now I'm not using it yet, so maybe, okay, Mauro said we should do test-driven development, so let's write the test first. Let's remove that. And let's implement that after we wrote our test. So how should we use that? Take impl. We pass in a cursor, numbers from is a cursor, and like this is the first field in this aggregate. So we pass it here, and then how many are left, or how. This depends on how much we want. Let's say 5, right? So left in this concrete case will be 5. The cursor will be these numbers from to cursor, and it doesn't compile. That's what we expect because dump. So we're passing this to dump. Dump wants a cursor. This thing doesn't look like a cursor, right? Missing some functions. So this is a cursor, but probably not the one that we want, right? What do we expect here? What is our expected output? Any guesses? 2, 3, 4, 5, probably 6, right? Or we want to take, that's how I would implement it. We'll implement it now. We take 5 numbers from the cursor. We start at 2. Okay, what is wrong? Okay, it's doing 2's forever. First of all, forever that's not good. So this is this false that we just copied. What should we put here? Probably we are done once left is 0. So this number is how many are left, and when are we done? We are done when left is 0, right? I mean, if you want to be careful, you can do this, or in case something weird happens, but this should be enough, right? It looks good, right? 5 values. But only 2 was the problem. Here, next, right? Next, we just decrement our counter. We should also actually move our cursor that we are wrapping to the next value. Nice. Now this is not a very very nice interface for our take. Let's give it a nicer interface. You will see in a minute or two why the other interface is nicer. If you're coming from functional languages, then maybe it's obvious. So let's write this as a function object. This const expert doesn't really matter, inline, because probably this is going into a header, and we don't want to repeat that name in multiple places. And let's call this take, and we pass some lambda to it, which does this something that we now will put here. So first of all, we write something. So take should take how much we want to take. Right? For example, let's do this. Now, how do we use this? We can use this take function by like this, right? So take is a function object. It contains this thing. The thing is a lambda. I call this lambda with 5. So inside here, this n will be 5 in this call. It does nothing. What we want is have something that takes a cursor, because then we can do take 5 of numbers from 2, for example, like we did below. How do we do this? We write another lambda that takes a cursor and does what? It returns take impl of this cursor and n. And what's the problem? N is not captured. Oh, it's a very nice error message. It directly tells us what to do. We need to capture this n from outside into here. Okay, we are actually not using it here now. Let's delete this and put it here. Take 5 of numbers from this. It's slightly better interface, so you will see soon why it's better. What else can we do? For example, I don't know, we can take these 5 numbers and square them. How do we do that? It's relatively simple. It's again something that takes like this iterator, for example. This cursor. And wraps it into another cursor that does the thing. Now, squaring is a bit too concrete. Let's do something more generic. Let's make a transform function. You know std transform? It is applying some function to all the elements of iterators. Okay, let's do that. I will copy a bit of stuff to be a bit faster. I copy the take impl and write the transform impl. I will again take a cursor and now a function. And what do? Okay, I want to apply this function to every element that I get from the other cursor. So first, let's do that. We call fun of cursor.get. And this stuff probably looks different. So here I just advance to the next one, and here I stop whenever this other cursor is done. Does make sense? Let's again do this. Transform, what does it take? It takes some function. Let's move this function, I don't know what it is, let's better move it into didn't write what fun is, right? So it's whatever. We could try to find the concept of what this function should be, but let's not do that now. So I take whatever function and I move it into this other thing, and this other thing will accept the cursor, and then I put this into transform impl. Let's move the function, and just because it's better. Now we will look at the cursor. Here we take all this cursor by value currently. Let's see if that is a good idea later. Okay, what can we do with this thing? We can transform. We put some function here, and then transform this cursor. And this cursor is a cursor that does numbers from 2, wraps it into the take 5 cursor, and then do transform. And what is, okay, we want to square it. We need to find the function that does square. Something like this, right? And now somewhere I forgot exactly where I am, the semicolon, right? Okay, that is nice, that works. Okay, are you still there? Is it good? It's a lot of fun doing this, so you should do it yourself. So let's look at one thing. Let's look. Well, what do we do? Let's take that again. Take 5 of numbers from 2. So what this does is it prints 2, 3, 4, 5, 6, right? I copy it, prints it again. Now, what happens if I instantiate numbers from here and put it into n, and I pass it here? Does this work? Probably it works. Prints the same thing. Now basically, so I have this cursor, right? This cursor here is now an L value when I pass it here. What do we do inside? I probably don't remember, or maybe you remember because I emphasized it 2 minutes ago. What do you expect to happen if I do this again? I don't know. We can go to the take. Here is the stuff where things are happening. Problem is here I take the cursor by value. I don't know if it's a problem, right? That was my choice. But what we should expect is that this prints again the same thing, because I pass in n is copied, n is numbers from 2 in both cases, because I don't modify n here. I take the copy here, right? So can we do better? Better in the sense that, let's say, if we have some L value and to a cursor, and I put it into take 5, it takes it by reference, because then what we would get here in these two calls is 2, 3, 4, 5, 6, 7, 8, 9, and so on, right? Let's say we want to do this, so we need to improve our code around take. So take should take the cursor by universal reference, so the forwarding reference. So we can, in case the thing is an R value, just by value, I forward this as value. I take the copy, and in case this is a reference, I forward it as a reference. So how do we do this? Forward, right? So I think we didn't mention how to forward this thing, because there's no concrete type here, right? How do I get the type of that thing? It was on some slides that you get the type by saying decl type. So I get the real type of that thing, so it can be reference or value, and I forward it in the right way. There's an alternative which makes this pattern a bit nicer now, so we can actually put here a template parameter like this. We say template parameter, which is a cursor, we call it C, and then we put C here. We don't have to write decl type here. But still not working. So what are we doing? So here at this point we are doing aggregate initialization of that thing. But what is the thing? The thing is ctat deduced, so class template argument deduction, and it deduces C to be value. So we have to say very concretely what that thing is. So this C here should be C reference in the case it's a reference, right? So that's what we express here. Okay. Now it works as we want it. We can do the same thing for transform. Not sure if probably don't do this now, but if you want to have transform work in the same way, you should also make sure that you perfect forward the cursor here, right? Okay. Where are we? Okay. And what is the time? It's the correct time. Okay, good. Okay, let's go back to this thing. Okay, this is my longest cursor transformation thing. Let's actually make this a bit shorter. Let's say square is this thing. So now basically I made a more concrete version of transform. We call it square, right? And that's why this pattern is nice. I can basically already say, this is now concrete algorithm, the square algorithm for cursors, right? So square takes a cursor, and what does it return? A cursor. We actually discovered a new concept, which is cursor algorithm. Things that take cursor and return cursor. Square is 1. What other do we have? We have take 5. Right. takes a cursor, returns a cursor. We can, if we like, we can also give it a name. Doesn't really matter, right? We can square the whole thing again. Can you see? Yeah, here, right? And then we can, I don't know, take 2. So we can write bigger and bigger algorithms of individual pieces. We have 2 algorithms only here. Or, well, take something and square, or we can combine it into something bigger, right? So what we actually, we are composing algorithms, but it is not maybe the most readable syntax. A bit too many parentheses here. So can we improve that? Would be nice if we can, for example, do something like compose, and we take a cursor algorithm, another cursor algorithm, another cursor algorithm, and another one, and then we apply it to cursor. That's so we are doing test-driven development, right? We test first. This is what we want to have. It's not very precise. I mean, we're just writing a test. This is not test-driven development. Okay, so we want this function compose, right? It's basically mathematical function composition. You compose functions like in math. How does that thing look like? Let's remove this, because then we are closer to the code that we are writing. So it looks like we need a function that is called compose. Which one? No, take 5 I'm not using. Okay. How do we do that? So what do we observe here? Right? To compose is a function that takes any number of arguments. So it's the pattern that we have seen in the morning, I think, in John's presentation. So there will be some variadic thing, right? So let's start like this. So we take something and more of something. And I don't know what we return, let's say auto. And then there's compose, and it takes f, so the first function. Now let's do perfect forwarding where we can. And more stuff. Here, right? By the way, I don't know if everyone, but you can write type name here. It's the same thing. Class is shorter. Okay, what does compose do? So I want to take the first, f, and then I want to compose all the rest. More or less, right? Let's improve that. Okay, so at some point, I don't know if there's actually the error that we will get here. At some point it will, at some point here we get an error that says our candidate function compose that we are calling here expects actually one argument, but we are passing 0. Why is that? Because at some point, so we recursively call this function, at some point we have consumed all the cheese and there's basically nothing left. Right? So somehow we need to stop at some point. So we have another function compose, which just takes 1 and it doesn't call compose again, right? Otherwise we will still recur. So what in the last thing, so what is composed of just one function? It's just the function, right? So we just return it. So I mean, here we were still not very careful. Sorry. It's the rough idea of what we want to do, but it's not complete, because what in the end, compose in the end, if you look here, should take a cursor. So we need something that in the end can take a cursor. And what we do is we return f of the composition of all the cheese, and then in the end apply the cursor on it, right, in the right way. So now, what is f? F is that f from outside, but we don't have it. Let's move it into that lambda. So moving here is getting this perfectly forward is a bit more works. Let's not do that. And then let's already compose here. Maybe we can write a new function which is already the composition of all the cheese. So where are we? So cheese is still not there. But now we have already cheese already composed. So maybe this. Oh, maybe we're missing a semicolon somewhere. And let's see. Yeah, that works, right? So now we have a function that can do composition of cursor algorithms. So like, this is now a new algorithm. Let's cut this here and say my algorithm. Now I can apply this algorithm whenever I want. Okay, and then that's we can do. Okay, we can do many things now. So one thing is we can improve syntax, because I don't know if some of you already saw the ranges library. We will see it tomorrow here. But the ranges library has a nice feature which allows you to pipe algorithms together. It allows you to do something like the following. You do numbers from to. You pass it to take 5 and dump. This looks pretty cool, right? So let's do this. We put it in a separate namespace, just a bit out of safety, because we will write an overload of this operator, of the pipe operator, or was this bitwise OR operator, but we will use it as something else, right? And we will write a relatively generic operator. So there are many things that actually might accidentally call it when we don't want to. So let's better protect it here and only use it when we really want. So if you want to use something from this namespace, you do using namespace pipes. Okay, what should this thing take? So probably return auto, and it takes some function g, some function f, and it does f of g. What is the problem? Let's look at that. It's interesting. Okay, wait. There's another error. Still, let's do that, right? So, what do we get? Okay, yeah, this is the one that I. Yeah. Okay, so this is related. This is related to something that that Michael probably mentioned earlier. So we have so the operator, pipe operator is called with take impl. That makes sense. Like this thing, actually take impl of numbers from that whole thing, and unresolved overloaded function type. And what's the problem? The problem is dump. This function here is a function. Functions are not first-class citizens, so we cannot pass it around. So let's upgrade this to a function object. So this. Is this the problem? No, just have to wait. And we're missing a semicolon here. Okay, now we messed up somewhere. let's see if that is expected, right? So something goes out of scope. So that is just a test, right? So this is not expected. So probably somewhere we messed up with our perfect forwarding. GFG. So what? Let's simplify it. Let's see where the problem comes from. Okay, this still works. So somewhere in the take, we have a problem. I'm not sure if I can find it now. This is the risk if you do this live. Do you see it? I mean, it's I forward it here, so ideally we should get this here. So you have a solution to my problem? This takes it by copy.
Yes, so dump is void, or return type of dump is void.
Okay, and probably. Okay, here. I think here's a problem, right? I take this. Okay, I return this, right? This is I take probably. Okay, here's the problem, right? I take this by value, but here at this point when I pass it to f, this is an L value, so we'll take a reference to that thing. But when I return this, this will go out of scope, right? So it's because I was lazy, right? So it's a problem because we can perfectly forward everything. I thought I take shortcut, I should not do it. But what is this? Deckel type of G. Deckel type of F. So now I do it everywhere. Deckel type of G of G, right? So this. Yes. Good. No. Cheating. Yeah. Okay, good. Okay, is that all? Unfortunately not, because I cannot write an algorithm with this, because I want to also write algorithms in that way. Oh, this works. Why does that work? No, it will probably not work. Oh, this works. So I'm not. I confused myself now. I don't know. Okay, there's one other thing, right? Yeah, that's the thing I wanted to do. My algorithm actually, this is not an algorithm, right? Why is that not an algorithm? Is it? Why is it not an algorithm? A cursor algorithm, right? Cursor algorithm is the thing that takes cursor and returns cursor. This one doesn't take a cursor. It is already a cursor, right? This is a cursor. I pass it to a cursor algorithm. What I get here is a cursor, right? This is a cursor. So I expect that to work. So what I wanted to do is actually the take 5 and dump. Take 5 and dump. And then I want to do take 5 and dump. Of what? Of a cursor. But it's already not working, right? So this is already brown. So what are we trying to do? We are trying to call dump with take 5. Well, dump takes a cursor. We are passing a cursor algorithm. So here's a problem. So we need something special in the case where we are actually just composing algorithms. Actually, we did something, it's called compose, but now we have to check when to do this. There's a nice thing, if const expr. So in one case, whatever that is, let's do it soon. We do this, and in the other case we do compose. Probably we do compose of f, g, and probably we have to be careful again of forwarding stuff properly. Does this work, forwarding? I'm not sure. Okay, we are anyway moving here, so here we can already move, right? Okay, what do? We check if f of g works, right? Because the problem here is f of g doesn't work. So what we can do is invocable f with g. Invocable, so this invocable we, right? This is a boolean. What is the problem? Okay, that's because in some other version that I wrote, right, I had an f and a g here because I did this, right, and then everything looks nicer. G plus f, g, f, everything gets shorter, right? F, G. Okay. Okay. Is the output expected? Yes, because we just made this take 5 and dump algorithm, but we didn't apply it to anything. So let's take numbers from 2 and pass it to take 5 and dump, and it works. Okay. There's another variation, what's the time? There's another variation of that thing, because now I used if const expr, but we also learned we can do concept constraints. It's actually, this is not perfect, right? What we allow here is everything where I can do f of g. Probably we could constrain it to only cursors. Should we do that? There's many other things we can do, right? Do you want to see how that looks like with a concept constraint? Okay, I think someone wants to see how that looks with a concept constraint. So how do we do this? Let's copy it. Okay, let's keep that for later, in case we mess up. Okay, well, what do we want? So we want, in the case where G is a cursor, we want to do f of G, right? In the other case where there are cursor algorithms, we want to compose as we do here. So there is the general case which does this. It's still, I mean, that part is still not better. There's an exercise on the repository where we can try to find the cursor algorithm concept. Then we can constrain this G and F also, right? But now it's not there. So we have two functions. Now they are the same. There's a problem, it's a redefinition. Now what did I say we want in the case where G is a cursor? I want to do this. I hope that works. It works, right? What did we do here? Right? There are two overloads. One is generic, G and F, and one is constrained that the G is actually a cursor. So in the case, is that actually, yeah, we still have the example that tests this. So when G is a cursor, so this numbers from is a cursor, so I go into this one, right? And I call actually take 5 and dump with numbers from 2. Right? So I never show this, but you can also still call this algorithm like this. Okay. Okay, this. What else can we do? Okay, I have 3 options, and we have, I don't know, we'll leave at the end of today like 15 minutes for questions, for the questions that we have on Menti, or I can also do half an hour if you like. So we have 15 minutes until the Q&A. I have 3 options. One is doing type erasure. The other thing is using customization points. And third thing is use a range-based for loop in this place. Right? It's a bit ugly syntax. Right? It would be nice if we can write for we colon cursor and do stuff. So these are the 3 options. Which one do you want? Who wants to see type erasure? 1, 2, 3, 4, 5, right? Who wants to see customization? Oh, come on, this is the most interesting. Oh, come on. Who wants to see range-based for loop for the cursor? Okay, so we do type erasure. Why do we do type erasure? Okay, sounds cool, yes. Okay. So the reason we do type erasure is because someone wrote this very complicated algorithm which takes a cursor and does something very complicated. It takes forever to compile. It does dump of cursor. Now we can call this very complicated algorithm with something like let's say numbers from to and take 5. Let's remove that stuff. And we also want to call it with, what was the name of the first thing that we had? Very concrete cursor, right? Okay, so we call it 2 times here. So that thing gets compiled 2 times because this is templated, and so it needs to instantiate it for every concrete type. So if this takes a long time to compile, it will take, like, every time you pass a different cursor, we'll have to compile it. So you cannot put it into a CPP file. It will always stay in the header, this thing, right? This very complicated algorithm, because you have to instantiate it with all your cursors. And the cursors, they easily change. It's not that, I don't know, have a cursor of int. It's actually the very concrete cursor. Here's the numbers from to, which is wrapped into a take 5 cursor. So there are just many, right? We put take 2 here, again another cursor. So what do we want to do? All our cursors so far operated on int. That helps. So let's take any cursor of int. And now we have to, because you decided you want to see that, we have to implement any cursor of int. So now actually both these things we should be able to wrap into this any cursor of int, right? Hopefully at some point when we did this, we can again class template argument deduce, so we don't have to say int. Do we have to? Oh, maybe we have to, because probably it cannot be deduced. Let's see. Okay. The problem is probably now, the only problem is that we don't have this. Okay, let's implement any cursor of int. It's your choice, right? It's the it's the most boring of all of them. Sorry. What do we? Okay, we do a cursor. We want a cursor of t, right? In this case, of int. You don't want to rewrite this any cursor many times. You want to at least should work on all the cursors that give you back something. Oh wait, what did I say? I don't remember what I said. It should, if we have different cursors that return different types for get, it should still work. Then it would be any cursor of, I don't know, string, char, whatever. Okay, any cursor. Okay, well, what do we do here? So you need to make it a cursor. Let's copy some functions from somewhere. So, okay, we don't, I mean, that makes sense, right? We don't know what we will do here. That's we have to do at some point. Is this a cursor? Let's check. No, there's a bit of noise here. Let's remove that stuff. You can already see here that it's not marked as an error. So it is a cursor. Also, it's not. I mean, there's still a warning, right? No return statement in function returning non-void, which is for this bool done. We promised to return at some point a bool. We don't do it yet. It's just a warning. Okay, let's put this back. We know we have to do something. It's definitely not the cursor that we want, right? Okay. To do type erasure, we need to define some interface, abstract interface that we can later concretize with a concrete cursor. How does that interface look like? Let's say, okay, this. Okay, let's say this interface. Okay, first of all, let's add a virtual destructor. That we don't forget it later and the wrong object gets destroyed. I mean, we're not doing object-oriented programming here, so all this dynamic polymorphism stuff that you know. And then let's add some more pure virtual functions. For example, one that returns t and get and const. And virtual bool done const and virtual void next. Okay, this is our abstract cursor interface, and now we actually know how to store the cursor. We store it in a unique pointer of this thing. And at some point, once we know how to initialize that, we can actually use it. But now we already know what we should put here. But before, let's include the unique pointer from memory. Okay, what do we do? Okay, we store some concrete instance at some point of a cursor, of this abstract cursor interface here, and this cursor, what does it have? It has some get done next methods. So we do impl. We are in get, do get. And here's a mistake, right? We cannot return with this any cursor of t anything. We can only return t's. And we should return. And we should do next on our cursor. And we should return done from our cursor. Okay, there's already a problem that we can fix now. There's use of deleted function any cursor int when I pass that thing to dump. Here was the problem. Well, I mean, there's so many details, probably it's hard to spot the problem. I mean, now we have a unique pointer in any cursor, so we can actually not copy it. Because unique pointers actually, you can only move it. That was from yesterday. So here, here we construct this any cursor of int, and we are passing it to this very complicated algorithm. Let's remove one, but so we should move it into that thing. Is that yes? Yes, because here we construct this any cursor, and it contains a unique pointer. We are.
It's inside your algorithm. It's already an R value.
Oh yeah, it's an yes, like this. And the other point where we are, so here, up to here we get it in the right way. Now here we actually, dump is taking that thing by value, and so we currently be doing copy here, right? So we should move it here. That is unrelated to what we are actually doing. Okay, we are one step further. Now what is the problem? We are not actually initializing this thing. No idea what, right? So we don't have it yet. So this is the problem, is it? Somewhere. Could not convert very concrete cursor to any cursor of int. So there's no constructor here. Let's add a constructor to any cursor. What do we want to pass here? We want to pass any cursor. I mean, not any underscore cursor, but whatever cursor we have. So cursor C. And let's copy it here. I take it by value. And now we have to do something here, right? We have to somehow get this cursor into that thing. Because if we manage to do this, then we are done. So, but it doesn't work because, I mean, now we do default construction of that thing. There's a null pointer inside, but we are already calling get, next, and done on this null pointer, so that's expected. Okay, let's put something in. Now, we have only an abstract interface here. Now we need to make it concrete. How do we make it concrete? We implement this abstract interface like this. And what we put in this thing? We need to store a cursor. What is this cursor? It's a cursor. And how does the implementation of these look like? So the get, what does the get do? The get does return cursor get. The done does what? The done does return cursor done. And the next does return cursor next. It doesn't have to return. That's cursor next. And now we would like to do, okay, this is, we would like to just create a new impl of whatever, of this cursor. Unfortunately, that doesn't work. I mean, I want to place it here, but this is now not an aggregate because it's inheriting from abstract base class. So we actually need to write a constructor here. So we need the constructor, which takes what? Takes cursor and places it in, let's do this, and places it into this cursor here, right? Like this. And now let's see if we missed something or if that's already good. Probably we have to, is that the problem? Do we have to say that this is a C? No. So what did we, my favorite mistake. Okay, first of all, I'm not using a lot of runtime polymorphism, so probably I should write here somewhere. Is that the right place to write override? You should do always, right? As you can see. Exactly. So now, if I would have written override here, then I would have seen this earlier. Forget it, right? So it is now a completely different function. This get is not this get because we are missing a const. Where does this go here? Yes. It works. So this was your choice, type erasure. And now we can pass any cursor of int to this very complicated algorithm. And I mean, the thing is now this is a concrete function, right? We can put it into some library. We can compile it once. It works for all cursors of int. So it works for this one and should also work for this one. Good. Now we have 10 minutes left. And there are 2 more interesting things to do, but unfortunately we cannot. We can do another time. Are there any questions somewhere? I mean, I guess towards the end. I mean, this is basically, it's just a pattern applied. Yeah. Wait for the microphone.
Hi. For the type erasure, so if I remember where you were explaining that if we don't do it, there's going to be multiple, we're going to compile that long functions multiple times. I don't know if in this tool, can you get like compilation time and just kind of see whether with type erasure, the compilation time actually dropped?
I don't think you will see that because, I mean, my very complicated algorithm is not that complicated.
Okay, yeah.
Right.
Yeah.
So, I mean,
At least you just get the one. You should see the different process. Yeah, you should see the assembly code.
yeah.
At least that one you can see. So everything.
But I mean, I mean, I can still. I mean, if I don't wrap it into, or I mean, if I call dump instead, then it would be the example. Should we do it? How do I get that's the problem that I always have. Who can give me here a window? More maybe. I want a new window.
Add new.
Add new. This
I
sounds.
think it's there.
Yes.
And
Yes.
list all the things.
Yes. 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 It's probably.
Probably able to
This is
do it
all
also in
what
the
we
other
need.
one.
Okay, so I mean it's very long, right? Already. So this is. So let's remove this. We should ideally remove everything that is not related to this problem. Okay, let's see. We have 560 lines of code for that, and lines of assembly, and 840. I mean, there are instantiation of that stuff, and I don't know. Should I optimize that to inline more? I don't know if we can make up the good example, but okay, let's copy that once. Okay, we have 848, and now now we do only dump of that thing. I don't know if that really will illustrate what it's doing. Now let's remove this and see if it shows what we wanted to show. This should be longer. It's actually shorter. So now you can optimize more, and I'm not actually using my. Okay, I should at least instantiate once any cursor of int, right? I'm not sure if that is.
I think that in case we can have an hands-on about type erasure and use let's say a simpler example with standard function, and maybe tomorrow we can have a look and show that multiple things get instantiated if you don't use type erasure. Yep.
And in general, the thing is that you can have template creep, so that everything becomes templated. So in some cases, you want to avoid that everything is a template and is instantiated every time with that you have different parameters. If you have type erasure, from that point on, you have just once.
So one point about this. So one thing is bloat, another one is compilation time, and there are actually tools. Just like you can profile your applications to see if they're performing well, you can actually profile the compilation process. So Clang has a flag, I think it's ftimetrace or something like this, where it outputs a profile, and you can open this in like this Chrome profile viewer, and then you see how much does the just the parsing take, how much does the instantiation take, how much do the optimization passes take. And we've used that because it can become quite a big problem if you have a big templated program. I think you know when you're at that point that you actually want to start profiling your compilation time. Like you'll notice it if you're getting frustrated waiting for things to finish compiling, then it's probably the right time to look at this.
Just as an example, our library, we experienced this problem because it took like 14 minutes to build. So we started checking why it was taking so long.
Comments on just the topic here. Or for me, the two main takeaways is, one, there are lots of useful techniques here. And I think there are many applications where you can actually apply these things. But the other equally important takeaway is don't re-implement these things. This exists in the standard library, and you should just use those. But you'll see tomorrow what that looks like.
I click once through this summary, right? It's basically to summarize what we did and what we didn't do. Right? We started with the cursor concept, more or less, as you have seen. Then we discovered these cursor algorithms. We did the composition of the pipes. And we didn't do this, and we did type erasure. It was different topics, right? And yeah, as Michael says, this is the idea of ranges, what is behind this, but yeah, it is already done, right? You need to find another concept